I was actually thinking a little bit how much homotopy theory, how much motives. If this is like the line between motives and homotopy theory, most talks are here, and maybe Thomas Nicolaus would be here, and I would be in Shinjuku. But I modified it a little bit, and I hope you're really going to enjoy this story. So what is really interesting, the theme of this workshop is motives. Motives grew out of large motivating thing is applying ideas of algebraic topology to algebraic geometry. But what I will tell you about today is when the story actually goes the other way around. Just in the past few years, there's been an explosion of ideas in homotopy theory proper coming from motives specifically. Let me talk a little bit about the chromatic homotopy theory, what kind of things it does, what kind of thing does it study, the motivating problem, and the one that still to this day very much looms over the whole field is the calculation of the stable homotopy groups of spheres. And one reason this problem, there are external reasons why this is something that's important. This measures the way we can map spheres into each other, but because any spectrum can be built out of spheres, it also measures what kind of objects are possible. This also, to some extent, measures topology of finite complexes in a stable range. And the other, perhaps more psychological reason is that this is just really, really difficult. This is how the stable homotopy groups look like in small degrees. We have pi 0 given by the integers. This measures the degree of the map between spheres. Now we have pi 1, z mod 2. This can also be interpreted appropriately, but then it becomes really quite difficult. We have a z mod 2. The pi 3 is z mod 24. Then it's 0, 0, z mod 2. After that, we have a z mod, oh gosh, I practiced this so many times, 240. Then we have a z mod 2. By now, you might think that perhaps all of these groups are cyclic, generated by a single element. They're not. Now we have a z mod 2 squared, z mod 2 cubed, a z mod 6 out of nowhere, and a z mod 504. If you compute the first few ones, and already this turns out to be quite complicated, unless you use what used to be very complicated if you try to use topology rather than things like arithmetic. But these groups have no apparent pattern at first sight. They're very complicated, and if you ask ChatGPT or any other modern AI conversational to continue this sequence, I assure you it will not get pi 12 right. Although maybe it will. It's a scary thought, to be honest. Hopefully it wouldn't get it right further than humans can right now. So to try to compute this using topology alone is quite difficult. The idea of chromatic homotopy theory is to relate these things to arithmetic instead. So here's the slogan, which sums up most of ideas of chromatic homotopy theory, is that the structure of stable homotopy theory is described by the moduli stack of formal groups. The first connection, and these a priori seem quite far away from each other, between stable homotopy theory and formal groups was made by Quillen. Arguably, the first person to really start using ideas of arithmetic was Jack Morava, and the slogan itself is usually attributed to Mike Hopkins, who popularized it very much by writing lecture notes in the 90s. So how do we connect these two things, or maybe what is a formal group? The notion of a formal group is classical, and I think goes back to the work of Lazard, or perhaps even a little bit before in the 1950s. But for the purpose of this talk, a formal group group is an abelian formal group scheme. Group scheme, smooth, one-dimensional. Smooth and one-dimensional as a formal group scheme. In other words, a formal group is an abelian group object which locally, as this formal scheme, looks like the spectrum of the power series ring. So how do we produce such things? Where these were first invented as an appropriate replacement for Lie algebras in positive characteristic. And the way they relate to those, if you have an actual group scheme, smooth of dimension 1, G, smooth one-dimensional, and it will be actually automatically commutative in this case, then you can look at the formal neighborhood of the identity, and this G hat here, the formal completion of the identity, is a formal group in this sense. So G here can be something like GA, GM, or an elliptic curve. And I believe this is actually known to be an exhaustive list of one-dimensional smooth group schemes, but it is not an exhaustive list of formal groups. Not every formal group, in fact, most of them are not of this form. So now, how do you relate formal groups to stable homotopy theory? Well, one more example. Suppose I have a commutative algebra in spectra, and I know that its homotopy groups are in even degrees. This is what we now call an even E-infinity ring. This theme is going to come up a little bit later. In this case, we can look at the cohomology of CP infinity. And it has a group structure, it has a ring structure induced from the multiplication of A, and it has a cogroup structure coming from the multiplication of CP infinity. This is actually a formal group. What is interesting about this construction is that very often we can actually recover the whole commutative algebra in spectra just from the knowledge of formal groups alone. This link here, this association discovered by Quillen is very tight. There are many things that this formal group tells you about A, and very, very often it allows you to recover the whole thing. Now, if the homotopy groups of spheres were concentrated in even degrees, then we would be very happy, and then we could use the formal group of the sphere, and maybe we could compute them. But of course they are not. In fact, this fails as quickly as it possibly can. Already pi 1 is non-trivial. So the idea here, the sphere itself is not of this form. It's not an object we can understand using formal groups. Well, we resolve it using things which we can understand using formal groups. So the idea is to resolve the sphere using A with pi star of A even. Now, when you have a resolution, in this case it's going to be some non-abelian analog of a chain complex, a cosimplicial object, you get a spectral sequence. And the spectral sequence we get in this case, it will converge to the stable homotopy groups of spheres. And you would hope that because these objects here were tightly connected to formal groups, perhaps the E2 term is also something related to a formal group. It doesn't quite work out like that, or at least it's not quite a formal group over any single scheme. What you get here is the cohomology of the object which parameterizes all the possible formal groups. You get here the cohomology of the moduli stack of formal groups. And the gradings are a little bit weird here. This is going to be T minus S, where S is the cohomological degree. Let me, yeah?
Could you explain what this resolution means, the resolution of the S means?
Right, there's a cosimplicial ring spectrum starting with the sphere and where all of the other objects are like this. and it's canonical and universal in a certain sense. This is known as the Adams resolution. Let me put some subscripts here. There's a lot of cohomology theories appearing in algebraic geometry. This really is quasi-coherent cohomology. And this is a certain line bundle on the moduli formal groups. In fact, this is the Lie algebra, which is one-dimensional, of the universal formal group over this thing. This spectral sequence, which is very important, is known as the Adams-Novikov spectral sequence. And what is really, now I'm going to do a party trick, something you can entertain your guests with if they're interested in chromatic homotopy theory. Already the knowledge alone that there exists a spectral sequence like this, it really starts putting order into the chaos here. Here are some facts about formal groups one-dimensional, which were known way before stable homotopy theory, were already known due to Lazard. And here has these facts about arithmetic. Formal groups are really arithmetic objects influence stable homotopy theory. For example, in characteristic 0, all formal groups are isomorphic. They are isomorphic and they have a very small automorphism group. They have the automorphous group given by the multiplicative group. And from this we can deduce that if you look at this cohomology, let me take it with all coefficients at once, and you tensor it with the rationals, there's almost nothing left. There are just rationals left in degree 0, 0. And that's exactly what we see here. This is also the same as the stable homotopy groups tensored with the rationals. In other words, the fact that all of these groups are finite beyond the 0th one is explained by the fact that the theory of formal groups is very, very simple in characteristic 0.
How do you see that the twisted cohomology is only here?
This was not the first time I almost fell off the stage. Don't worry. Yeah, question?
How do you see that the twisted cohomology with that line bundle is also
It has, it's a cohomology of the multiplicative group with coefficients in non-trivial character, and that also vanishes in characteristic 0. So only the trivial character contributes something. That's a very good question. And this was actually known before chromatic homotopy theory. That's a theory that's, this is known as Serre's finiteness. And he proved it using slightly different methods. So this was known before, but now something more interesting. In characteristic P, formal groups are classified by an invariant called height, which is a positive integer or infinity. There's also infinite height. So, and this gives you a way to approach homotopy groups of spheres by studying this cohomology. And now this cohomology group, we can stratify using the height filtration. The height, the notion of the height induces infiltration on this stack. And this is what allows it to divide and conquer the calculation. Instead of trying to do it all at once, we do it one height at the time. And this is how it is usually done these days. And here's the party trick part, if you want to impress your guests. Let's see, in this small range, only height 1 contributes anything interesting. Height 2 appears a little bit later. And there is something special about formal groups of height 1. Namely, if G is of height 1, then the Lie algebra of G tensored P times is the same as the Lie algebra of G. Now, if you move it to the other side, another way to write this is if we tensor the Lie algebra of G with itself, P minus 1 times, then this is trivial. This is just OX. So there's this number here appearing, P minus 1. And this gets doubled here because we divide by 2 in the part of line bundle. So somewhere here we should see 2p minus 2. And we really do. This is the fun part. Here, this is the first 2 torsion. Here, Z-mod 24, that's 3 times 8. This is the first 3 torsion. The first 5 torsion appears in degree 240. This is the 7th stem. First 5 torsion. And finally, the first 7th torsion appears here. You can converse yourself the formula for this, that the first p torsion is in degree 2p minus 3. And I really like this example. It's something you can see immediately. If you just show this to ChatGPT, it might not guess that we have a pattern like this, but in fact we do. And better yet, we have this beautiful pattern, but it's explained. It's something we understand now. The pattern itself was known, this one, before the connection to formal groups was discovered, but it's easiest to understand it. Where is this 2p minus 3 coming from? Is this p minus 1 appearing here? Questions? Yeah?
How did you get 50 minus 3 and 50 minus 3?
That's a good question. There is a doubling here because this is t over 2. So it's actually 2p minus 2. But it actually lives in the homotopy of the sphere mod p because you want to be in characteristic p. In the sphere mod p, it's in degree 2p minus 2. The boundary map moves it up by 1. So let me talk a little bit how these ideas, and that's something that was discovered only very recently, connect to the theory of motives. As the motivation for some of the things I will talk about, let me talk about a very classical theorem which predates a lot of these things. Let's look at the algebraic K-theory of the complex numbers. That's something that is known. Pi 1 is the units in the complex numbers. But it is still quite complicated. This is I meant to grab the colorful one. This is known, but this still carries deep arithmetic information. The homotopy groups of this spectrum is the algebraic K-theory of the complex numbers. It's a little bit involved. But this maps by endowing complex numbers with its natural topology into complex K-theory. And this is now something that is actually much more accessible by a theorem of Bott. The homotopy groups of that is a Laurent polynomial ring. The complexity visible here does not appear if we take the topology of the complex numbers into account. This is the one big difference. From the point of view of topology, complex K-theory is not particularly difficult. And a deep theorem, and a very interesting theorem due to Suslin's rigidity, implies that this comparison map is an equivalence after P completion. This tells you that all of this interesting and intricate information visible here disappears as soon as we P-complete. It's the rational part, which is the one that is not visible in any completion, that contributes to the complexity of algebraic K-theory. And this is a theme we saw before, something that Ryomei mentioned in his talk. If you work away from the characteristics, cohomology theories tend to behave the way they do in topology. For example, they are A1 invariant because A1 is topologically contractible. And this is something we see here. This characteristic 0, so any prime is away from the characteristic, and things simplify tremendously as soon as we P-complete.
What if we replace C
With,
R?
is it an equivalence or? and we map it into topological real K theory.
For example,
That's a good question. I don't know.
What is the question? What is the question?
What if we take the real numbers and map into real topological K theory? Maybe someone in the audience knows, but I will continue. What's the guess? It's an equivalence.
means after the order,
Yes.
So here's a little bit more involved construction in this vein, where we're going to see something happening in the category of motives after P completion. So let's look at motivic cohomology of the complex numbers. This is also the units in the complex numbers. And now we can consider the long exact sequence. This is all motivic cohomology. This is multiplication by P. And mapping into here, we have H1, H01 with coefficients in Z mod P. Now, the multiplication by P map is surjective on units in the complex numbers. Everything is a P fruit, but it's not injective. Inside here, we have a P fruit of unity, and this is in kernel of this map, so it gives rise to a class here, which is often denoted by tau. This is a class in motivic cohomology, mod P motivic cohomology of the complex numbers, but one can show, and this is where you need to use a little bit more involved methods, that tau lifts to a map from the motivic sphere to the motivic sphere. But because we're working with mod P coefficients, this map will also only exist after P completion. The existence of this lift is not too difficult from the point of view of algebraic topology. The method here is the Adams spectral sequence. But as an input, this takes the structure of the motivic Stinod algebra. So you still need to know a little bit. You need to know the motivic Stinod algebra. That's a calculation due to Wojewodzki to show that this lift exists. But now, here's a theorem. And this is, in fact, a sequence of theorems and ideas. So I will list quite a few people who are involved in one way or another in proving this theorem. Starts with Wojewodzki. Then we have Levin. Then Isaacson. And Gorgi, Wang, Xu. There's a lot of people because there isn't a single source where this would be stated exactly in this way. It's either stronger or slightly weaker. But here's the theorem. Well, the first thing is we have a non-trivial map of the motivic sphere. What happens if we invert it? If we invert the motivic homotopy groups, it turns out that motivic homotopy groups, which again a priori should encode something, an arithmetic of schemes over C, their geometry, you actually only get the ordinary P-complete homotopy groups, and then you have to tensor with this tau. This thing is bigraded, this thing is single-graded. You obtain a new grading by attaching an invertible variable. This is what happens when we invert tau. Now what happens if we take the quotient? 0p mod tau. So the cofiber of the multiplication by tau map, this turns out to be the cohomology of the moduli stack of formal groups. Up to regrading, and everything is P-complete here. It's actually going to be the P-complete moduli stack of formal groups. And finally, we have a spectral sequence converging to this side, the homotopy groups of the tau-inverted sphere, by using the tau-Bockstein filtration, by filtering this using powers of tau. And the claim is that the tau-Bockstein spectral sequence is isomorphic to the Adams-Novikov spectral sequence. And that's already, Voevodsky was the first one to compute the Steenrod algebra. And this allows you to create tau as an element of the P-complete sphere. Levine was arguably the first one. That's a beautiful paper to notice that the slice filtration, which is related a little bit to the tau filtration here, has something to do with formal groups. And these are very recent theorems where, in fact, Georg Wang and Shu put an algebra structure on this and describe the quotient. Here's how this looks informally. You start with motifs over the complex numbers, and you P-complete. And that's still very large because it's generated by all smooth schemes. So we pass to the cellular part, the part generated by the sphere and P1. So these are very few motifs of algebraic varieties do belong here. We only put the minimal amount of generators. What happens if you invert tau? And this is actually true at the categorical level. You just get ordinary homotopy theory. You get the category of spectra. If you kill tau, if you set tau equal to 0, what you get here is the theory of formal groups. These are correspondingly parts 1 and 2. What happens if you invert? What happens if you kill? And now part 3, the fact that these arise in this way, the middle object, which is a categorical deformation, relates these two sides. And this connection here is the Adams-Novikov. It's the Adams-Novikov spectral sequence of chromatic homotopy theory. Any questions here? It's taking so much time, I should preemptively do this everywhere. So, notably, both sides here really belong to the realm of ordinary homotopy theory. We have spectra, we have formal groups, and we have the spectral sequence relating them. Well, the construction of this is quite involved. It involves starting with all cellular smooth schemes, P-completing, enforcing this Nesvich descent and A1 invariance. It's really quite involved. But now you can ask, is there a way to construct this thing, which is really quite involved, in a way which only uses stable homotopy theory, which does not use the theory of smooth schemes? And here's the observation which is going to guide the construction I'm going to show you is that the cellular part is generated by S00 and P1. If you look at S00 and you take the complex points, that's just the zero sphere. And then if you take P1, which is S21 complex points, that's S2. And the observation here is that both are even spheres. And this makes you feel that perhaps motivic homotopy theory, or at least the cellular part, is something that you get if you only allow even spheres as generators. So let's do that. And this actually works very well for an arbitrary ring. That's a recent discovery. So let's say R is an E1 ring. In other words, it's an associative ring, not necessarily commutative. We will not need the commutative structure here. And we define a subcategory of perfect even R modules. This sits in the subcategory of all R modules. And this is smallest subcategory with three properties. One, well, two, is that the even shifts of R. So if you like S0 and for the sphere S0 and S2 are inside, they are perfect even, and two closed under extensions plus retracts. So another name for this category, which is almost quite right, these are the R modules which have a finite decomposition into even cells. These are the things you can build using even cells. I closed under extensions, but I did not close under cofibers and retracts. In particular, this is not a stable category. That's going to be quite important. Here's a definition. And well, let's say even synthetic R module is a functor X from this category, perfect even R modules, into spectra, which preserves cofiber sequences. This is an important point here. If you take all perfect R modules and you ask the functor to preserve cofiber sequences, the color you're going to get is just R modules again, or perhaps modules over the opposite ring, to be precise. What makes this interesting is that this category is not stable. It's not true that any map here can be completed to a cofiber sequence. We ask it to preserve those which already exist in the category. This is one way you can think. We're using this category as generators. How do you generate a category? Well, you pass through presheaves. That's how you construct the motivic category, where instead of perfect even R modules, you would start with smooth C schemes. Now what we do is we enforce some relation. We want those cofiber sequences which already exist to be preserved in this new category. And here's the theorem. I think it's very neat. Those things define a category, a subcategory of all spectral presheaves. And the theorem is that if you look at synthetic spectra, so you do this construction where R is the sphere, this is the same as the motivic category after P completion. In other words, this gives you a description of the P-complete motivic category, the cellular part, purely in terms of homotopy theory, but even better, you see exactly what is going on. This thing is generated by the even spheres, and there are certain relations between those. That's what's going on. Any questions about this theorem?
Doctor,
Yeah.
do you know what happens if you plug in T of Z there instead of spectrum?
This is the next line is what happens for other rings. But which ring did you say?
D of Z.
DOC. Nothing interesting. But and we'll see why.
Sorry, what is it?
Yeah. Mm-hmm.
Sorry, what is it?
The category of synthetic synthetic S0 modules. Yeah. And this equivalence, let me just mention this a second, but the proof actually uses the work of the people mentioned there, of Wojewódzki, Levine, Korgwang, Isaacson. You need to know quite a bit about this to prove this. Because the way you do this is you show that this thing also fits into a diagram like there. And that's actually not so difficult. So that and once you know they both fit into a diagram like this, and that's quite involved on this side, then it's not so hard to construct an equivalence. So Vova's question, which I will answer now, is what happens if instead of the sphere we put a different ring, for example, the integers? Well, this category always is a deformation of the category of R modules in the sense that it fits into a diagram like this. And deformations are described by filtrations. So what you're really asking is there's some filtration on R. What is it? Let's make this explicit. So one thing to note here, this category, and that's similar to what happened at the beginning of Aravinstock, it sits inside all additive functors. Into spectra. But the inclusion of this category has a left adjoint, which I'm going to denote L, and this L is actually T exact. It's not so clear from the way I define this, but this condition of preserving cofiber sequences is actually a sheaf condition for a certain topology, and this is the sheafication functor. Now you make a definition. The perfect even filtration on R, and that's going to be a certain filtration on R encoded by this functor. Well, what are we going to do? The nth piece of this filtration, what you can do is you can use R to define a pre-sheaf on perfect R modules by looking at maps into R. And that actually does preserve cofiber sequences because you're in a stable category. Now what you can do is you can level-wise truncate it. Take the level-wise Whitehead cover. And after you do that, it will usually lose this property. It will no longer preserve cofiber sequences, so you have to sheafify. You apply this L. And this is now another synthetic R module. It's the Whitehead cover in the category of synthetic R modules. You evaluate it on R. It's a little bit strange the first time you see it, I admit, but that's a way to get a filtration on the ring, or any R module, in fact, from this category. Now, it's not too difficult. Using the fact that any perfect even R module is generated by even cells, you can show that this category itself is generated by even cells, so it can be written as modules in filtered spectra. This category is the same as modules over the filtration of R in filtered spectra. For the sphere, the filtration you get here is the Adams-Novikov filtration, and that ties everything to chromatic homotopy theory. Now the question is, what is this filtration for a ring in general? We see it encodes the whole category. Well, here's an example, and this is where we're going to answer Vova's question. What if R is even? So we tie up to the right blackboard. R even. Well, on an even ring, there are no interesting perfect even modules. They are all free. That's because if you have two even things, the extensions between them are controlled by odd homotopy groups. So you have no odd homotopy groups, then every perfect even module is free. And that means that every cofiber sequence between perfect even modules over an even ring splits. So this condition is actually very weak if your ring is even. You're just asking for additivity. And from there you see that this category is very simple and the filtration is very simple. This is just the Whitehead cover. In other words, our even rings, this filtration you get from the category of even R modules is just the Whitehead filtration. There's nothing interesting going on. Now, that's actually very good because there's another filtration mentioned briefly by Thomas, which also has the similar property on even rings. So as a consequence, what you can do is you can map the perfect even filtration of R. You map R, let's assume R here is E infinity. So R is commutative. We're going to map R into E infinity rings, which are even. And you have a map into filtrations of those even E infinity rings, which is actually this one, 2n. There's a canonical map. Oh, sorry, that's not an equality. There's a canonical map from the perfect even filtration of a commutative ring into the limit of the Whitehead filtration over all even rings. And this thing actually appeared briefly. This definition was made last year. This is the Hahn-Raksid-Wilson even filtration. And what makes this filtration very remarkable is that it only depends on the structure of a commutative ring in spectra, but it recovers many motivic filtrations if you apply it to a spectrum of motivic origin. So this, for example, this gives the BMS filtration on things like complete THH, or complete TC, or complete TP. So, yeah.
One quick question. I mean, if you just, let R be the sphere and you take an arbitrary module, what's the filtration you get?
On this module,
Like,
it will be the Adams-Novikov filtration on this module.
Okay, that's what I was coming.
And it's going to put high
Yeah.
entry even cells into other way, right? It's not the classical filtration.
Yes, it will be a slight regrading. But this, just between us, I only put 2n there and not n. It's because this is how things are often done in commutative algebra. But I think for, say, non-even, the better definition would be to have this larger than n, and then it would be exactly, I think, the standard one. Let's talk also a little later. There is, you're rightly pointing out, it will be a slight difference there. Okay, so this filtration is very interesting. On things like THH, TC, it recovers the BMS filtration, draws from this structure of this as a commutative ring, without using things like, resolving without knowing that it is actually THH of anything. You just know it's a commutative ring spectrum. But now, the perfect even filtration maps into this one, but it's a little bit different. It only depends on the E1 structure. It only depends on the category of R modules. And here's the theorem. Let R be a commutative algebra in spectra, which admits even faithfully flat. That's a technical condition. Flat map into an even infinity ring. You should think this condition is saying, and this was introduced by Hahn, Raksid, and Wilson, that R, perhaps not even itself, can be resolved by even infinity rings. And again, this covers things like the sphere, but also THHP complete, or TPP complete, or also ordinary Hochschild homology, in which case the even filtration is the Hochschild constant Rosenberg filtration. Then this filtration here is the same as the even filtration, as the Hahn, Raksid, Wilson. And what makes this really, really interesting is that unlike for an ordinary algebra where a ring is either commutative or not, to make an even ring into E infinity ring, it's not a property, it's a structure. And it's actually a very, very tough thing to do most of the time. The corollary of this is that for these E infinity rings, the filtration depends only on the E1 structure. And that itself is a little bit reassuring, and this is something that appears in Thomas talks. For example, this tells you it's actually functorial in E1 maps. Even if you already have two infinity rings, maps of E infinity rings are very complicated objects, but for this class of rings, the filtration is actually functorial in maps of E1 rings. Any questions about this theorem?
Sorry. In the corollary of the computer part,
This?
is R assumed to be an infinite algebra?
Yes. This is, you could make this definition for E1 ring and put maybe index over E1 rings, but the Hahn-Rexed-Wilson filtration is something that you should do for E infinity rings. Okay. And here's a question that's a natural question to ask you. You can ask, is it always an equivalence? Are those two filtrations always the same? They are not. But to find an infinity ring for which they differ, you really have to take something like a free infinity ring. In other words, it's not something that naturally arises by, let's say, in motivic homotopy theory. And I would argue in the cases where they do differ, at least in this one example, this filtration is more explicit and is easier to understand than the even filtration. Here's one, we have 10 minutes. I'll give you one example. Another thing that homotopy theorists care about very much, and this is a theorem of Hahn-Wilson, just published last year, is we have this height notion, and there's a notion of a height, but again, it can be very hard to make something into an infinity ring. Things that arise in homotopy, in motivic homotopy theory, are usually infinity, but there are many things which are not infinity and cannot be made infinity in homotopy theory. The perfect even filtration then gives you a way to define an even filtration using only the E1 ring structure. The Hahn-Wilson theorem tells you that the algebraic K-theory of a spectrum called BPN, and this is something that's height n, is height n plus 1. And this is an instance of chromatic redshift. Taking algebraic K-theory increases the height of your ring. And this is the first time a chromatic redshift was proven at arbitrary height. Before that, we had examples that had 1, 2, and I think a little bit at 3. So that was a huge breakthrough. But what's important is that this thing can only be made E3. And it's already not so obvious that you can do that. So what they do is they make the ring into E3. Then they want to use trace methods. Yeah.
We currently can only make it.
Yes, we can only.
We cannot prove it.
Right now. And for small n, you can sometimes do better. So yes, this is the minimum known. We know it cannot be made E infinity, though, for example. What they do is they use trace methods. So they study, they start with THH of BPN, and they equip it with a certain filtration. And this filtration comes from some very specific choice of map from a mu. But this filtration they use, you can show is actually this one. In other words, in the one solid example we have, where someone studied a motivic filtration on something like THH of BPN, this was in fact the perfect even filtration here, which is another piece of evidence that this is quite the right filtration to study in the non-infinity case. time this uses another way, I think, mentioning a story, the even filtration was really, of Hanraxid-Wilson, that was a huge breakthrough. And one big fan that is my co-author, but on a different paper, Lars Hesselholt, is in particularly a big fan. And one way he explained to me the meaning of the even filtration is as follows, that the even filtration, or any kind of motivic filtration on THH, where we have, maybe I just remove THH, it comes from geometry. For example, it can come from perfectoid covers. But another way he interprets this is that when you have geometry, you have a symmetric monoidal structure. So, and this is exactly what happens. The motivic filtration on THH depends only on the E-infinity structure. It only depends on the symmetric monoidal structure. And this is one way to see that this is geometry. But the perfect even filtration tells you that you can weaken it quite a bit. To see geometry, you just need an E1 structure, or perhaps you need an E1 structure on THH. That means your ring needs to be E2. So it really narrows, expands our meaning of what it means to have geometry. One last thing I wanted to do, which is a little bit orthogonal to motives, but I want to convince you how you can measure progress of the field in terms of stable homotopy groups, and that these methods, in fact, are related methods of deforming categories had a huge impact. So here's a progress in stable homotopy groups. In other words, how many stable homotopy groups were known at a given time. So I'm going to make a little table here. Let's see, starts with 0, 10, 20, 30, 40, 50, 60, 80. Okay, and let's see, this is going to be a little bit historical. The first discovery that these things can in fact be non-zero was made, I believe, by Hopf, who discovered the Hopf vibration. And this was roughly in 1920s, 1930s. And 1930s late is also when Pontryagin computed the first 3 ones. So here, 3. This is 19, I'll use colors. This is 1930s. We were at 3. Then you actually had to wait a little bit to get all the way to 10. The first 9 of them were computed by Serre in 1950s using the Serre spectral sequence. And in particular, what I really wanted to do this is, there should be a bigger gap here. The next advance was really all happening in Japan. This was when Toda started making calculations in 1960s, very serious calculations with the EHP, long exact sequence, which appeared in the talk by Aravind. And he got all the way to, I believe, 19. And a little bit further later than 1960s. What is very interesting is, and this is what made Toda really such a powerhouse when it came to calculations, Toda would compute stable homotopy groups by computing the unstable ones first. This is also what Serre did. But around the same time, the Adams spectral sequence was invented. And that was a huge jump all the way to around, then we have, yes, Toda, all the way to around 45. This was the consistent use of the Adams spectral sequence and the May spectral sequence, mostly by Maholt and collaborators. By Maholt, Tangora, May was involved in the invention of the spectral sequence. And finally, in the 1990s, a little bit further, and that's Kochman invented a method of using the Atiyah-Hirzebruch spectral sequence. And he got, in his book, he got roughly to 64, but some of those are not quite right. Roughly up to 50s with some corrections. He got everything right. And the big breakthrough, and you can really see the time passing here, was Kochman was using computers. Kochman and Bob Brunner really started using computers to, for example, compute the E2 term of the spectral sequence. And of course, this is around the time where you could actually fit a computer in a room to do something like this. And you can see this is actually where things stayed for a long time. The 61st group was computed around 2018. This was an Anna's paper by Wang and Xu, where they compute the 61st group. But you see this is a wonderful paper. They invented a new method, but the groups were roughly known up to this range, and it took 3 decades to nail 61st. Here you really see how the difficulty of doing this grows and grows worse. Things become much worse, and every single group becomes quite a challenge once you get so far. So you can ask, this was 2018, only 5 years ago. Where are we now? Where are we now? After the discovery to motivic homotopy theory, and after the discovery that it's often useful to encode the spectral sequence using a deformation, like at the very top. That was the big discovery. Well, this is roughly where we are today, a little bit past 61, somewhere in mid-90s to 100, I believe. This is a big jump in just 5 years. This is an upcoming paper by Isaacson, Burklund, and Xu. And this all started, this huge jump. It's almost a vertical line, considering where we were in 2018. It all started with this discovery of motivic homotopy theory. I think this huge influence the idea started with Voevodsky and Grothendieck before him had on algebraic topology is not as well known as it should be, but it's huge. It's a generational jump in the knowledge. And I started grad school around 2015, so I was there to witness all of this, and it's something wonderful, and it's something that really brightens my day every day. Thank you so much for listening.